Okay, students. So now we are going to observe wave motion. To observe that, I have a slinky here. One end of the slinky has been attached, whereas I can move the other end of the slinky. If you all look at these coils, relate them to the particles of the medium. So when I give a disturbance, you all know the propagation of disturbance is the wave motion. So I will be giving the disturbance from my right side and observe how the waves travel or how that disturbance propagates through the medium. That is what we call as the wave motion. So here initially when I give a disturbance like this, can you all see how the particles of the medium are moving? You can see the particles moving this way where they contract and relax, or they come closer and get far away. That is the movement of particles. I will explain the waves in detail later. So now you can see how the disturbance is propagating. So here you saw that the wave moves in this direction and the disturbance also moves in the same direction. So this is one type of wave which is called the longitudinal wave. And since this needs a medium for travel, it's known as a mechanical wave. The same way, we can generate the disturbance like in the surface of water in a different manner. Now you can observe how these waves are moving. Here you can see a different movement in the medium of the particle. You can see the wave motion going like this. So this is also a mechanical wave, but the way the particles move, it's a different type of wave, and that is known as a transverse wave. So students, you have observed the slinky being moved, and you can see that the particles of the medium move and there is a propagation of the wave. And this is what we call as mechanical waves. Okay, students. So now we are going to observe the second type of mechanical waves, the longitudinal waves. So again, we are going to use a slinky with tapes attached at certain points so that you can easily observe the slinky. So here again, as I told you all before, these are the particles of the medium. I am going to generate the disturbance from this end so that you can observe the wave motion from here to there. At the same time, observe how the particles of the medium vibrate or how they move, the direction and the way they are moving. So now I'll generate the disturbance. Here you can see the movement of particles. When you see darker regions where the particles come close to each other, we call them the compression. And the lighter regions where the particles are far away are known as the rarefactions. Now observe the wave again. You can see how the compression and rarefaction are moving along the wave. The second one, observe what happens to these particles. Are they moving away or along with the wave, or are they just vibrating from their point? Observe that carefully now. What is happening to those particles? You can see there is a vibration to those particles, but they don't move along with the wave. So that is what is a mechanical wave. Particles don't move, but the wave propagates and energy transmits with the wave. And here, this is the direction of the wave movement from my right to left. At the same time, particles are also vibrating parallel to them. So, the direction of wave and the direction of movement of particles are parallel to each other. Then what are these types of waves? They are longitudinal waves. So finally, again I will show you the wave motion. Observe carefully. You can observe all the properties of the longitudinal waves. So students, with this activity, we can confirm that the wave that I generated now are longitudinal waves. Okay students, now I am going to do this activity to demonstrate that sound needs a medium for propagation. Or in other words, sound does not travel through vacuum. So to do that, I have this glass jar, that is a sealed jar, so that only the air that is present inside is there. Air cannot go in, but we have connected the jar to a vacuum pump. When I on the switch, the air will be drawn out. So with time, there will be nothing inside the jar. So it will become a vacuum. And here you can see the bell. And this is where you will see the movement of the bell, and you can see the hammer hitting on the cap, and you can feel the vibration. And this part is connected to the electricity where we have the batteries all connected. So when I connect the wire here, electricity is supplied and the electric bell will start to function. Then you can hear the sound clearly. Afterwards, when I on the switch for the vacuum pump, you can observe the electric bell moving, but you can feel the sound decreasing. So observe carefully. Now I will connect it to the power supply. Here you can see the vibration as well as you can hear the sound. Are you all able to hear the sound clearly and observe the function of the bell? Yes. Now I am going to on the vacuum switch. Listen carefully. Okay students, still the bell is working, but you can't hear the sound. Initially you were able to hear the sound clearly. Then what happens? The sound became faint, and then when the bell is still ringing, you were unable to hear the sound. So when air was drawn out, it became a vacuum inside the jar, and because of that, you couldn't hear the sound, but you saw that the bell was working continuously. So from that observation, we can confirm that sound needs a medium for propagation, or else sound cannot travel through vacuum. So now we are going to do this activity to observe how the physical properties affect the nature of sound. To do that, I have two blocks here. You can either clamp the blade with the two blocks and then vibrate it. Here I am going to just hold on to the top block so that the blade doesn't move, and then I will vibrate the blade. So here students, in your book, they have given the length of the blade to start with as 10 centimeters. But in this activity, I am going to start it with 5 centimeters. Here you can see, if I measure it, the length is 5 centimeters. So with that length, first I will vibrate the blade. I have to hold it tight. That is the reason if you clamp it, it will be easy. Otherwise, we can hold it tight like this. So now when I vibrate the blade, listen to the sound carefully. You can hear the sound of the blade. You can see it vibrating. So that is the sound when the blade is short. Now I will increase the length to about 10 centimeters. Here you can see, students, it's almost 10 centimeters. So the length of the blade has become double. Now I am going to vibrate it again. Now you can hear the sound again. Can you all feel a difference between the two sounds? Yes. Again, I will increase the length to about 15 centimeters. So here you can see it's the length of a short ruler, so it's 15 centimeters. Now again, while holding it tight, I'll vibrate it. You can see the vibration. Can you all hear the sound clearly? Yes. Now you observed and heard the sounds when the blade was 5 centimeter in length, 10 centimeter and 15 centimeters in length. Were you all able to differentiate the sound? Yes. So the reason is when the length of the blade increases, the frequency of the sound decreases. And frequency is related to the property called pitch. The pitch of the sound decreases when frequency decreases. I'll repeat that again to you all, students. When the length of the blade increases, frequency decreases and the pitch decreases. So that is why first you heard a slightly higher pitch sound, then the pitch decreased and now the pitch was the lowest. So from this activity, you can understand that the properties of the wave are related to the nature of the sound. Okay, students. Now we are going to observe how the pitch of sound is affected by frequency. So to do this activity, I have tuning forks here. Now this is a tuning fork, you know that. So here when I vibrate this, if I can feel it with my hand, I will feel the vibration of the tuning fork. So you know what vibrations are, and these vibrations generate sound waves. So even if I knock it here and hold it near my ears, I can hear the sound. And also you can see these are of two different lengths. The longer one has a frequency of 256 Hz and the short one has a frequency of 512 Hz. So you can see when the size of the tuning fork is shorter, the frequency is higher. So to observe the relationship between the frequency and the pitch of the sound, now here we are going to use an oscilloscope, but this is not the normal oscilloscope that we use in the lab. So instead here I have the application that is similar to an oscilloscope. So on the screen you will be able to observe the shape of the waves. Now as I talk, you can see that there is a pattern, a wave pattern on the screen. So that pattern is due to the sound waves that are generated by me. So likewise, you will be able to observe how the frequency changes when we change the pitch of the tuning fork. So first, I am going to use the long fork. I am going to strike it on this rubber cork and hold it near the mic. At that moment, you all have to observe the screen to see how the waveform is generated. I am going to strike the tuning fork and hold it near the mic. Observe the screen carefully. I will strike it again. One more time. Okay. So you have observed a certain frequency with the long tuning fork that has the 256 Hertz frequency, and this is of a slightly lower pitch compared to the small tuning fork. This has a higher pitch than the previous one. So now observe how the frequency is. Again, I am going to strike the tuning fork. I will strike it one more time. So when I use the tuning fork with 256 Hertz frequency, that is a somewhat lower pitch compared to the other one, you would have observed the frequency. When I use the second tuning fork, that is shorter and of higher pitch, you would have seen that the frequency of the wave was higher. So from this observation, we can conclude that when the frequency increases, the pitch of the sound increases. Okay, students. So now we are going to observe how the loudness of sound changes. You already know when we talk softly, the sound is less. If I talk loudly, the sound is more. So that is what referred to as loudness. And when I am talking, if a person is standing next to me, they can hear the sound louder. That is because the energy contained in my sound waves are higher. But if it is a person far away from me, they will hear me with less loudness because the energy carried to that person is less. But I am not going to demonstrate the effect of energy on loudness. Instead, we are going to observe how amplitude changes the loudness of sound. So to show that there is a relationship between amplitude and loudness, I am going to use this drum here. I can just tap on the drum like this, or I can use an object. Normally they use a stick. Here I am using a pen to tap on the drum. So you can hear the sound. But if I hold the microphone near the membrane and when I tap lightly, you know the sound will be less. At that point, observe the screen. Already I have told you all, this is not the original oscilloscope, cathode ray oscilloscope. Instead, we are using an application that is similar to the cathode ray oscilloscope. So here, when I make a small sound, I will make it again, then observe how the wave forms on the screen. Can you all observe the waveform? Again, I will do it with a soft sound. Now, I am going to make a louder sound. Again, I will make the louder sound. Okay, so what did you all see? You were able to see a small amplitude when the sound was with less loudness. But when the sound was more louder, you were able to observe a larger amplitude. So that means when amplitude increases, the loudness of the sound increases. Okay, students. So now we are going to observe the property, quality of sound. When I am talking to you, you can identify my voice. When your friends talk to you, you know their voices. When you hear the sound of music, you know from which instrument that music is coming. So that is known as the quality of sound, and that depends on the shape of the waveform. That is the shape of the sound wave. So to show that, I have a tuning fork here and a flute, and also I have a student playing the guitar for me. So first what I will do is I will use the tuning fork. As I did before, I will strike the tuning fork on the cork and hold it near the microphone. You can observe the waveform here. And also you all know we are supposed to use a cathode ray oscilloscope, but since we don't have that in the lab, I am using an application that is similar to the cathode ray oscilloscope. So I'll start off the activity with the tuning fork. I will strike it and hold it near the microphone. Observe the waveform. That is the quality of sound. I will strike it again. Did you all observe the waveform? Yes. So you know the shape of the wave formed by the tuning fork. Now we will get a student to play the flute as well as the guitar so that you can observe the waveform that is produced. So one of my students is here to play the guitar for y'all. When the guitar is played, observe the shape of the waveform in the screen. Are you all able to see the difference in the waveform? I will ask him to play again. Okay, student. So you were able to see the difference between the tuning fork, the waveform, and the waveform of the guitar sound. Now again another student is going to play the flute. Again the frequency 256, that is similar to the frequency of the tuning fork. At that point, observe the screen to identify the shape of the sound wave that is produced. Were you all able to see a difference? I will ask him to play again. Thank you. So here again you can observe that there were three different types of waveforms. All were sound waves, the same note. With the tuning fork there was one type of waveform. With the guitar there was another type of waveform, and finally with the flute there was another type of waveform. So that means the shape of the wave of sound is related to the sound that you hear. That is what you say as quality of sound, and that is the characteristic that is used to identify different sounds formed by different sound sources.